Okay, so this video is about the operations on complex numbers when they're in polar form. So some operations are easier when it's in polar form, some are harder. Okay, so just to remind you what we mean, r cis theta, this is polar, and z is equal to x plus yi is in Cartesian. Okay, rectangular, so that's another way. Polar is also called argument modulus form as well. It's got, some of them always have different names, that sort of thing. There you go. So if we have two, let's just go straight to an example. Let's see what we're adding. Okay, so if we've got 2 cis pi on 3 plus 3 cis negative pi on 2, that sort of thing. There's no easy way to do this in polar form. The only way to perform this addition is to convert each of these to their rectangular form, and then once you've done that, to add them. Okay, so look in the other videos, convert this first into Cartesian form by going to cos pi on 3 etc plus I sine blah 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 blah, doing that, and then doing the same for this one, and then just adding all the real and imaginary parts together, putting them back together. It's not easy, it's actually a really long process and quite annoying, and very similar for subtraction. Okay, so addition, not very handy in polar form, but where polar form comes into its strength is in multiplying and dividing. You'll remember how hard it was to, this should be an L, multiply and divide when it's in rectangular form, because we had to use conjugates and etc. But it's actually excellent. So let's have a look at multiplying. I'll prove this in class. But if you've got two complex numbers, both in polar form, r1 cis theta 1 and r2 cis theta 2, if you multiply those two together, what you get is you multiply the your two radiuses together, your two modulus, and then what you get in cis, your angle will become, these actually add together, theta 1 plus theta 2, and that's the rule for multiplying. So when you multiply two terms in polar form, you multiply the modulus and then you add the arguments together. Okay, really simple. Let's have a look at an example. Let's have 2 cis pi on 3 times negative 3 cis 3 pi on 4. Okay, that looks pretty good to me. Okay, so what this is equal to is you multiply the radiuses together. 2 times negative 3 is negative 6 cis, and then you add your arguments together. Pi on 3 plus 3 pi on 4. Okay, let's just neaten this up a bit by putting them both into, let's put them both over 12. Okay, what do we get? We get 4 pi plus 9 pi, so you'll get 4 plus 9, 13 pi over 12. And there's your answer. Or is it? Now let's just check this. Is your argument in between negative pi and pi? We need to just check that. No, it's not. It's gone too far. Okay, so here we're just a bit here, we've gone a bit too far. So to correct this, how do we correct it? We need to change that to negative 6 cis, and instead of 13 pi on 12, so it's just gone pi on 12 back over 1 too far, let's just change that to negative 11 pi over 12, because that's 1 pi short, 1 pi on 12 short of that pi there. So there is your correct with your argument. Okay, so the correct value there, and that's how you multiply numbers together. Let's have a look at dividing. Very similar when you're dividing complex numbers in polar form. So if we've got r1 cis theta 1 over r2 cis theta 2, you divide your modulus 1 over r2, and what do you expect to happen? Yes, instead of adding, you subtract theta 1 minus theta 2. So there is your formula for dividing. Again, let's have a look at an example. Let's go root 2 cis pi on 2 over root 8 cis 5 pi over 6. Okay, again, you divide those two first. So you got root 2 over root 8. Well, root 8 is 2 root 2. You can see what's going to happen there. They'll just cancel out, so that's easy. Cis, and then what happens is we just subtract your arguments. Root pi on 2 minus 5 pi on 6. Great, equals half. Your root 2 is cancelled. Half cis, and let's put it over 6. And then you're going to have 3 pi minus 5 pi, so that's going to be negative 2 pi, which is negative pi over 3, and that's within our argument range. Okay, it's between negative pi and pi, so that is fine, so that is all correct. I'll just rewrite it so it's clear. Half cis negative pi over 3, and that is your answer there, doing that division. Perfect. Let's just look at powers. We can actually use the multiplication if we extend that and keep going. Then if we've got cis theta, so we've got something in polar form, we want to raise that to the nth power, what that will be equal to is r to the power n, okay, and then cis, but theta doesn't go to that, it goes to actually n times theta. Okay, so the argument just multiplies by n, and this is called de Moivre's theorem. And it is very, very powerful in complex number realm. You can find out, do square roots, you can do powers, everything is very, very nice. Let's just look at an example for calculating a power. Let's just do, say, root 2, I'm just making something up, cis negative pi on 4. And let's just raise that to the 6th power or something like that. Okay, so here we go. What happens is the root 2 gets raised to the 6th power, and what happens to cis? Well, that gets multiplied by 6, so it'll be negative 6 pi over 4, so it gets multiplied by 6. Let's sort this out. What's root 2 to the power 6? Well, that's 2 to the power 3, so 2 times 2 times 2 is 8, so 8 cis, let's just simplify this, that'll be negative 3 pi over 2, and negative 3 pi on 2, is that within our range for an argument? Negative 3 pi on 2 is all the way around here, so no, that is not within our range. Okay, so there's negative pi on 2, there's 2 pi on 2, 3 pi on 2, oh sorry, it's there, oh, sorry about that, it's right there, so it's gone way too far. The other way to write that would be positive pi on 2, okay, so equals 8 cis pi over 2. That's what this answer would be equal to. And if you notice, if you've got an argument which is on one of these axes, so if you've got either 0, pi on 2, pi, or 3 pi on 2, then you're going to get simplified answers, because you look at the values of cis. Now, what's the value of cis 0, cis pi on 2? I encourage you to go find them out, because it's a shortcut. Let's just quickly expand this out to show you what I mean. Is if you think about it, cis pi on 2, it's going to have no real component. It's only going to have an imaginary component, because that's 8 cos pi on 2 plus I sine pi on 2, okay, which is equal to, what's cos of pi on 2? Well, cos of pi on 2 is going to be equal to 0, so that disappears. Sine of pi on 2 is equal to 1, and so what you're going to get is 8i. Isn't that good? So you get this big complex number, you raise it to the 6th power, and you just get 8i. And so that is de Moivre's theorem, and we'll go into a bit more of that into depth in the next video.